Hello, honors Algebra 2 mathletes. We are going to go through section 5.7 today and talk about a couple different theorems that we have been using kind of the ideas of for a while now, but now we're actually going to get them on paper and expand on them a little bit. First, or the theorem that we have in the box right here is the fundamental theorem of algebra. Basically, go through and read those bold words. A polynomial has at least one complex root. And so obviously we've known that in what we've dealt with. We have imaginary and we have real roots, but both real and imaginary are considered to be complex roots because the complex number system is made up of the reals and the imaginary. So the complex is the total number of roots. So, for example, a quadratic would have two complex roots. Both might be real, both might be imaginary. You can't have one imaginary because imaginary come in pairs. Let's expand on that a little bit with this corollary that we have here. Every degree n polynomial has exactly n roots. So that's actually what I just said before. Quadratic has two roots because it has a degree 2. A cubic, like the one in example 1, is going to have 3 complex roots. So we can answer, actually, the first part in example 1 is finding the number of complex roots. That's 3. So I'm going to put that down on my answer right here right away. This table that we have here is a table that represents the possible scenarios given how many different imaginary or real roots that we could have, knowing that total we can only have 3. So we have these possible scenarios here. Scenario 1, 2, 3, 4. We might not use all these, but I'm going to just put one down in the complex, one answer down in the bottom of the table there for complex to kind of start here. So scenario 1 would be that we have 3 complex, and let's talk about how many imaginary and how many real we can have. The most imaginary that we could have here is 2 because they come in pairs, so this has to be an even number. So since we can have total of 3, the most imaginary that we could have would be 2. That would mean that we have 1 real then. Now we want to go down by 2 until we get to 0 for the imaginary numbers. So we could have 0 imaginary. Again, we can't have 1 because they come in pairs. Well, that starts another scenario then. So I'm going to put a 3 down here, and then we could say that there must be 3 real. Those are the only 2 scenarios that we could have. So as I come down here to the answer, it says there are 3 complex roots, either blank or blank real. Because if you read example B, they actually don't ask us for how many imaginary, but we found that first. We found the imaginary first because we knew they come in pairs. So we use that to help us find out the different scenarios that we would have with our real roots, that we could either have 0 or 2 real roots. Now, the possible rational roots, that is from section 5.6, the rational zero theorem. That's where we found the values of p and q, where p was the factors of the constant and q were the factors of the leading coefficient, which is 1. Well, in this case, p over q is going to be equal to just p, since q is 1. So all of our p-values would be the factors of 6. Positive negative 1, positive negative 2, positive negative 3, and positive negative 6. We don't have the answers to this cubic right now, but if we had any rational roots, we know that they would have to come from that set of numbers right there. So the possible rational roots, I'm just going to rewrite that down here as part of my answer. 1, 2, 3, and 6, and their opposites. So the table helped us to answer the question, and kind of the key part of the table was getting the imaginary in there first, and then we could answer how many complex and how many real. The complex conjugates and irrational conjugates theorems we've used before. Basically, it's the idea of pairs, that both of these types of roots or zeros come in pairs. So let's start with complex conjugates theorem. Uh, that deals with imaginary numbers. We know that if a plus bi is a root, so is a minus bi. And if you have just a pure imaginary number like bi, then negative bi. So it's the opposite of the imaginary part. You know that they are roots together. If a plus the square root of b is a zero, or a root of the function, so is a minus the square root of b. These words here actually should be zero since we're talking about a function, but that's okay. Basically, if you know that they come in pairs, then you're good. Look more like a b. This is the irrational conjugates theorem. Okay, irrational numbers. So we're saying that square root of b is the irrational part. If we just had the square root of b, then negative square root of b. This you've used since Algebra 1 when you solved a problem like this. X squared equals 8. Take the square root. Obviously, we would simplify. But what's really important is that we knew that we had both positive and negative values as our answer. So let's use that in these two problems here. If two zeros are square root of 3 and negative 2, we're asked to find a polynomial function of least degree with real coefficients and then a leading coefficient of 1. And the leading coefficient of 1 tells us we don't need to worry about finding out what a is. All right? So here's the thing. The x minus 2 is a 0 tells us that one of our factors is going to be x plus 2. Because remember the idea that if k is a 0, that x minus k is a factor. Always the opposite. And with the square root of 3 that we have there, we know that negative square root of 3 is also a 0. So I don't know if you just want to put a plus minus in front of that, but whatever you need to do to remind yourself that the square root of 3 also tells us that negative square root of 3 is a 0. So that gives us actually two factors. X minus the square root of 3, which is from this guy, the original. And then because of the irrational conjugate theorem, we know that x plus the square root of 3 is also a factor. So what we're going to do is double distribute or FOIL these out. I have x times x. I have positive square root of 3x, or x squared to 3, and negative x squared to 3. And those are going to cancel out in the middle. And then what we're going to be left with is square root of 3 times negative square root of 3, which is just minus 3. So when you FOIL out those two green factors, that's the binomial that we get in return. I'm going to bring that x plus 2 down. And now we can finish by FOILing those out. Before I go any further, let me just say, once you get used to doing these, you're going to be able to probably just look at that 1, 0 right there. And without writing any of this, just know that that came from that factor right there. That and its conjugate came from that factor right there. So in other words, I'm okay if you skip, let's get rid of all this stuff here. If you just go right to that step right there. Okay. Although it's probably a good idea, I'm going to put this in the end anyways, but right away I'm going to put my f of x equals so that we don't forget. Actually, let me put that stuff back up here on the screen because I think it's a good idea to have that in our final answer here when we're done. But I wouldn't care if you just started with what I have as my second step right here. All right, let's distribute that out. And we get probably easiest here to just look at what degree we're dealing with. X times x squared is x cubed. Next, I'm going to want to get my quadratic term, which is going to be 2x squared. Then I'm going to have my linear term of minus 3x. And I'm going to have minus 6 as my constant term. Okay. In example 3, we're told that zeros are 2i and 5, so the 2i tells us that negative 2i is also 0. Let me take a second here to just tell you that in your homework, sometimes they will give you the full pair, so they'll give you both of these. You don't need to do anything then. You just do this the way they were about to do this problem. You just don't have to come up with the conjugates yourself. Sometimes they'll give you the pair of conjugates. In other cases, they'll do what they did here, where they just give you one and you have to recognize that the other one is also a 0. So I'm going to start with the factors here. We know x minus 5, and then we know x minus 2i, which is from the given 0, and x plus 2i, which is from the 0 that I just wrote in red right there. And this is going to be a function, so I'm going to write fx equals. Notice that when we do end up foiling these out, we're going to get, or distributing these out, we get 1 as a leading coefficient. We will in this problem too, and that coincides with what the directions say. Okay, so let's take a look at what happens when we multiply those complex conjugates together. Please don't forget that we learned a pattern for complex conjugates, a plus bi times a minus bi. Well, if we didn't have the i's, it would be a squared minus b squared without the i's if we didn't have those. But with the i's, I squared times I squared is negative 1, so we end up getting a squared plus b squared. So without the i's, it's the difference of squares patterns. With the pattern, and with the i's, it is the complex conjugates pattern. All right, let's see. F of x is going to equal. Let's distribute out our two conjugates first by using that pattern. It's going to be x squared. B in this case is just 2. All right, B in this case is just 2. So we don't need the I there. We just say it's a squared plus b squared. And as you look at what our original zeros were, those two red guys, you probably could just skip to this step like we talked about in the last problem. If I told you that 2 and negative 2 were zeros, you know that it would come from x squared minus 4. But if 2i and negative 2i are zeros, it comes from x squared plus 4. Okay, here's our other binomial, and we'll FOIL these out here. X cubed, and then minus 5x squared, and plus 4x, and minus 20. Okay, on the next page, we get Descartes' rule of signs. We're going to take care of that actually in the next video. What I'd like you to look at is the example, the last example in the packet or in the notes that you have, example 8, because it's similar to the problems that we just did. So example 8 gives you these two zeros, 2 minus I and negative 1. So the negative 1, it's easy as a factor, that gives us x plus 1. But the 2 minus side tells us that 2 plus I is also 0. Let's break this down, what happens with these as zeros. So we're going to have, I'm going to do this over on the side and come back to, just get a little bit more set up here, f of x equals. And in a second, we're going to get something here from those complex conjugates. All right, so let's come over here and break this down here. The x minus 2i, x, let me start over again. 2 minus I, let's start with that 0 as a factor. The 2 minus I is going to be a factor x minus, and then we put 2 minus I, the 0, in parentheses. The 2 plus I is going to look like this inside of its factor. So notice again, we have x minus the 0 as a factor. That's how we always write a factor. And in this case, the zeros were 2 minus I and 2 plus I. All right, I'm going to show you a little trick here. What I'm going to do is distribute those negative signs into those binomials that we have on the inside. So we're going to have x minus 2 plus I in this one, x minus 2 minus I in the next one. Now what I'd like you to notice first, as a shortcut, is this is always going to happen, where if we started with those binomials and then distributed the negative, look at the two binomials that we get back. it looks as if we didn't even have the parentheses around our zeros to begin with. Let me just write that without the parentheses. It looks like the binomials that we started with just without the parentheses on the inside. It's just that this one is here and this one is here. That's always going to happen. So in other words, if you want to skip that whole step where you write those parentheses and just write them out like this, I'm fine with that. Because when you distribute the negatives, they end up looking the same anyways, and it doesn't matter what order they're in because these are complex numbers and they also work with commutativity. So what we have now is these two what look like trinomials, but we're going to break this down a little bit more. We're going to group these together like this. Okay, we're going to group those together like this. Why? Because we have A plus B I and A minus BI here as our patterns. It's just that A is x minus 2 and B, which is the coefficient of our imaginary part, is 1. There's a 1 there and there's a 1 there. It's just plus and minus in front of it. So B is just 1. So we remember that this FOILs out to a squared plus b squared. So we know that a squared is going to be x minus 2 squared. And b squared is going to be 1 squared, which is obviously just 1. I don't know why I came over here. I'm going to come back over here. Okay, that's what that's going to FOIL out to, always. So this becomes x squared minus 4x plus 4, and then we have plus 1. So all together, now I can combine the 4 and the 1, we get x squared minus 4x plus 5. I'm going to come back over here and put that in as what I get when I multiply the factors of those two zeros together. Okay. Now before I go any further and actually FOIL that one out, let's just look at this x squared minus 4x plus 5 real quick. What if I asked you to solve this? Okay, x squared minus 4x plus 5 is not factorable. So what I would do is probably move that 5 over and complete the square. Okay, now this is not even something that you need to be putting in your notes right now. Just watch for a second. So I'm going to complete the square here. So we have x, and then we're going to take half of that negative 4, square it, and what we do to one side, we got to make sure we do to the other. So we completed the square, and we factored it. I forgot my 2. We factored it all in one step. On the right side of the equation, we have negative 1. So now if we're going to solve this, we're going to take the square root, and we get x minus 2 equals the square root of negative 1 is positive negative I, and I'm going to add 2 over. Look at the two zeros we get. That was a nice little check to make sure that what we had here was correct. Look at the two zeros we get, the original zeros that we started with. So we know that we did do this whole thing correctly to get the right trinomial x squared minus 4x plus 5. All right, we're going to put that up next to the x plus 1 and actually go through and just double distribute this out. This is the kind where I like to take the binomial in together. So we're going to get first, do it like this. We're going to get first x cubed plus x squared, and then minus 4x squared minus 4x, and then plus 5x plus 5. And we'll combine some like terms here. Get our final answer. X cubed minus 3x squared plus x plus 5. There's the trinomial that has these 3 zeros. We're going to finish up the rest of these notes in another video.